Okay, everyone, good morning. Just right at the top, I want to say this meeting is being recorded and will be available on our website. I'm Mario Loyola, Director of the Environmental Finance and Risk Management Program at the Institute of Environment at Florida International University. The Environmental Finance and Risk Management Program is a cutting-edge new program at FIU that hopes to combine the most advanced financial modeling with environmental data analytics and environmental law and policy to make sure that we in South Florida and we as a society are in the best position to deal with environmental challenges like catastrophic hurricanes, sea level rise, climate change, and others. The EFRM program will be hosting a regular lecture webinar series, of which this is the second. So please let me know if you'd like to be included in future events. My email is mloyola@fiu.edu. And please feel free to share any other comments that you may have about today's lecture. We will be hearing from two engineers of the South Florida Water Management District, whom I'll be introducing in just a moment, as well as Professor Yayantha Obesekera of FIU. After I'll ask Obi, as he's known to us, to open up with some comments. And then we will have two presentations by Owosina and then Hongying Zhao of the South Florida Water Management District. And then hopefully at the end, we'll have time for some Q&A. In the meantime, until the Q&A starts, if everyone can make sure to stay on mute, that'll produce the best results for our call today. We're delighted to have some of the most important engineers in South Florida at the Water Management District. Owosina is Chief of the Hydrology and Hydraulics Bureau at the South Florida Water Management District. He's a civil and environmental engineer by training with over 30 years of international, local, private sector government experience in water resources and numerical modeling. He oversees a program with over 80 engineers, scientists, technicians responsible for numerical modeling, hydraulics and hydrology analysis, data acquisition, processing, quality control, and archiving in support of the district's mission. Hongying has extensive experience in hydrology and hydraulic modeling, flood protection, level of service assessment, stormwater treatment area performance assessment, stormwater management system designing and permitting, and best management practices. She is lead engineer of the South Florida Water Management District. The South Florida Water Management District is a regional agency in the state of Florida that's responsible for the operation and maintenance of the primary flood control system in a 16-county service area stretching from Orlando to the north down to the Florida Keys. The primary flood control system, the Central and South Florida Project, was built by the U.S. Army Corps of Engineers starting in the 1950s, and several of the assets are approaching the end of their design life. These assets include canals and structures that are today experiencing conditions such as higher sea level and denser and more spatially extensive urbanization than were assumed at the time of their design. The South Florida Water Management District has embarked on an effort called the Flood Protection Level of Service Program to assess the ability of these assets to continue to meet their flood protection objectives into the future and to identify what adaptations are necessary to ensure a resilient flood control system over the next 50 years, considering continued urbanization, climate change, and sea level rise. So that's the present. So today's presentation will focus on the flood protection level of service. And some of you may have heard about it in recent weeks because it's been on NPR multiple times. I'm delighted. So welcome to Akin and Hongying from the South Florida Water Management District. I'm also honored to introduce Jayantha Obesekera, a colleague and professor at FIU, who has worked for many years with the South Florida Water Management District. Obi, as he's known at FIU, is the director and research professor in the Sea Level Solutions Center. He previously served as the chief modeler at the South Florida Water Management District, where he had a leading role in the modeling of the Everglades and Kissimmee River restoration projects. He was co-author of the Sea Level Rise Projections report published by NOAA for the National Climate Assessment, and was a lead author for the Southeast chapter of the National Climate Assessment. So Obi, thank you for joining us. Thanks to all of you for joining us. And with that, Obi, if you could share a little bit of your experience in working with the South Florida Water Management District and all the good work that we've done with them in that collaboration. I think that one of the takeaways that I hope students especially take from this call is just how important the collaboration is between the university and these crucial agencies of state and local government. And you know, if you're looking for ways to make an impact on the world and to make the world a better place, we need you to step up. So and the opportunities to really make an impact are closer than you think. So with that, Obi, if you could take it away, thank you.
All right. Well, thank you, Mario, for that nice introduction. You know, most of you, I recognize many names in the attendees list. Most of you know me as Obe, and I'm happy to be part of this program. Actually, you know, Sea Level Solution Center is in the Institute. So Institute as a whole, I think, have this complete programs where we can look at these regional scale issues and solutions holistically, not only looking at modeling sea level rise that we work on for the Institute, and also having this new program that Mario and others are directing. I was very pleased to hear that it's going to be part of the Institute. I have worked with the Water Management District, as Mario explained, for many years, and I understand the system reasonably well. I continue to work with the Water Management District with Akin and Hongying's group, primarily in the area of providing climate projections for planning and a level of service type analysis. We have a couple of projects. One is with Water Management District, working with the US Geological Survey on projecting extreme rainfall. And the Building Commission now has given us funding to expand that for the entire state. And I'm also helping to provide climate scenarios for the future. You know, we work with the Dutch quite a bit, and they have some nice program where they develop climate scenarios. And I feel this is a very important program. I know how much it could cost, and I'm sure Akin will talk about it to solve these regional scale problems. Financing is always a challenge in a kind of what I call non-stationary environment when the conditions are changing, and investment decision making is tough in that kind of environment when you look at the uncertainty. So, and one last thing, you know, a lot of times, you know, up to now, we have not looked at the system as a whole. And I think with this effort by the Florida International University and the Institute, we will be able to look at the system holistically. We work with the local governments and local municipalities and counties, but without solutions at the regional scale, I think our investigation or assessment for resiliency will not be complete because they're all codependent from each other. And I'm sure Akin will talk about that. And I worked with both Akin and Hongying in the past, and many of his staff. It's an excellent group to work with. All right, thank you. I guess I will hand it over to Akin or Mario. You.
Akin, please. Thank you for that, Obi. Akin, please go right ahead. This is going to be an exciting presentation.
Thank you very much. So when I first got the opportunity for this talk, I thought about it's a Friday, and who wouldn't like a nice detective story to go with, a nice whodunit? And I was going to structure the talk in a somewhat informal, almost playful way that still shared all the correct information that goes about the who, the what, the why, the how, the when. And I'm kind of glad I didn't use that approach because Mario did such a good job introducing, and Obi also, that everybody would have known who did it. So I took a slightly more serious look, but you'll see remnants of that initial approach in the slides. Also, I think Obi has been a little bit modest. I think Obi is a giant here at the district, and he put quite a bit of our modeling and almost everything we do on climate studies on the map. We're glad to still have engagement with him, and it's a critical piece of applied research strategy. So what I'll be doing with you all today is I'll be introducing you, as Mario mentioned, to the flood protection level of service, which is a key part of the district strategy for dealing with flood protection into the future. And I asked my colleague, Dr. Zhao, to join me and give a case study to help make the picture clearer on some of the things I'll just be speaking to. So first of all, who are we and what do we do? Okay. So the South Florida Water Management District is one of 5 water management districts in the state of Florida. We're the largest and the oldest. Our footprint covers the area from Orlando all the way to the Keys, and we support or represent more than 800 people scattered around 16 counties. Within this region, we're responsible for water resources, and our mission identifies 3 key areas: ecosystem restoration, flood protection, and meeting the water supply needs of the region. There's also a water quality component that's strong and straddles all of these mission elements. But today I'll be focusing on the flood control mission. To understand how the district tackles the flood control mission, it's important to understand what the flood control responsibilities are in South Florida and what the infrastructure looks like. We describe this as a 3-tiered system. That includes a primary system, the trunk highways and interstates, if you have a traffic analogy, that's managed by the district, my organization, and the U.S. Army Corps of Engineers. These are the water bodies or the conveyance systems that discharge water to tide, to the ocean or to the Gulf, and stores the bulks of the water that's used to meet the water resources needs of the region. This area provides service to the secondary system, often run by local governments and special districts. And those organizations and agencies discharge into the primary system to provide getaway capacity for the tertiary system, which is run by homeowner association, private landowners. And that's the system that many of you are very familiar with because you see it when you open your front doors or look at your back windows. To meet our part of the responsibility, we operate a system known as the sorry, I had a slight glitch there. We operate a system known as the Cnsf System, which is the Central and Southern Florida project. It was a system built by the U.S. Army Corps of Engineers many, many years ago, 60 to 70 years. And in areas where the Cnsf system do not exist, we run the regional primary system, such as in Collier County, on contract with the county themselves. The system we operate to provide this flood relief has more than 2,000 miles of canals and levees, more than 160 major drainage basins that we operate within. There are several control structures, well over 1,000, with 71 pump stations. We have large water bodies that we manage, including the stormwater treatment areas that provide some polishing and water quality enhancement as we send water into the Everglades system. And Lake Okeechobee is the heart of the system, more than 450,000 acre feet of storage, as well as the water conservation areas, which holds even more, part of the remnant Everglades, but allow the people that live on the eastern parts of the district along the coast to live there while water is packed to the west. So I'm not sure what the mix of the audience was, and thought I'll introduce just a little bit of description on how gated structures work. So if there's anybody who needs to get credits, take a snapshot of these slides, it will probably get you engineering credits for the day. So first of all, a number of structures that I mentioned are gravity structures. They lie along the coastline and they operate based on gravity, based on what's happening on either side of the structure. And what you're looking at is a section through a typical spillway. I'm not sure if you can see my mouse, but on the upland, on the inland side, the upstream side, you have the headwater elevation, which is typically the driving force. The section in the middle is the superstructure itself with the gate in red. And the section to the right side of your screen represents the ocean or the Gulf side and what we call the tailwater elevation. And during the rest of this talk, if I'm talking headwater or tailwater, just think headwater is typically the higher side, which represents the inland side, and tailwater is typically the lower side, which represents the ocean. And when you have the system that operates by gravity, water flows from the headwater side to the tailwater side. Okay, so how do we operate? At this gated spillway, what determines when we open or close the gates are the objectives of the facility itself. And these facilities serve two purposes. One, they help prevent saltwater intrusion. And for that purpose, we close the gate anytime there's a risk of water from the ocean side or the tailwater side going inland. We also close the gates to help, during dry periods, to help keep the water table high, to provide a positive gradient from the freshwater side, which is the inland side, towards the ocean side. Now, what happens during a typical rainfall is that as the rain falls, the water level on the inland side rises, and it gets to an elevation at which we choose to open the gate to prevent flooding, to allow some stormwater discharge. And that gate elevation represents the level at which we want the gates open. The rain continues to fall, we keep it open until the conditions change and the tailwater side starts to fall, and eventually the headwater side also drops. Eventually, the headwater side will drop to the point where it gets to a gate close elevation, and we'll close the gates again to keep the inland side wetted, to keep some water level in there, providing that gradient towards the salt side. So what happens during high tides or king tides that are getting more frequent, as well as with sea level rise, is that you have increased amount of time when your tailwater elevation gets higher than your headwater elevation. And under those conditions, to honor the saltwater intrusion prevention piece of the mission, we have to keep the gates closed. And that creates a concern, because if you have a rainstorm on the inland side during those conditions, you may have to keep the gate closed while water level rise above the gate open elevation, increasing flood risk on the inland side. So that is in a quick schematic that helps explain what's going on. Now, with that in mind, think about the conditions that we're facing. The data that I'm showing here is from the Key West site. I think it's one of the lengthier records that's available to us. It's an ocean gauge with some of the trending that's happened. But essentially what it shows you is that over the last 100+ years of record for this location, you have a rising or increasing trend in the ocean elevations. You're seeing the evidence of sea level rise. Now, this is the historic data, and Key West is often used because it's a lengthy record, but irrespective of where you look along our coastline, you see essentially the same type of signature. And these two slides are essentially duplicates, but what you're seeing in the image in the middle here are a number of ocean gauges that are available to us. And at a subsample of those, even with those with a short data set, you see the same trend in water level. So you are seeing evidence of sea level rise. Now that's what's happened historically. As we look at what might happen into the future, there are a number of different organizations or agencies that have made sea level rise projections. And within this region, in the southeast coast of Florida, there's the Southeast Climate Compact that has gone through the effort over the last many years and updated this product from time to time of coming up with sea level rise projections that the county compacts, the counties that make up the compact are comfortable using. Now, these consensus products combine information from multiple sources, including the Corps of Engineers and NOAA and other people's charts. What they represent, what the 4 counties and the municipalities that participate in the compact in the southeast part of our district believe are a reasonable range of projections that could be used for different types of infrastructure. The district leverages this information, and for our level of service work, we count on it to some degree. As you'll learn later though, we understand that there are multiple studies going on that use different projections, and we came up with an approach that doesn't rely solely on the sea level rise projections to do analysis, and I'll be glad to describe that to you. As I go through this presentation, I'll highlight some areas that I see as potential areas of potential opportunities to collaborate, because part of my excitement at doing this talk is I'm kind of hoping I'll inspire some of your students who are interested in maybe interning with us, or who haven't picked their research to do research that's beneficial to us. And so I'll try to kind of spend a little bit more time on some of those areas that represent interesting things we're looking at that could be of research interest. So you've seen what's happening with sea level rise. One of the things I want you to note as well, because we realized when we started doing flood studies, that was a critical piece, is what happens to groundwater with sea level rise. Now, when it rains in Florida, we have a high water table, but the first part of that rain goes to fill soil storage before eventually you get runoff. If the intensity is low enough, that ultimately we have to discharge. With sea level rise, you have a higher water table typically, especially close to the coastline, and you lose some of that soil storage. So the same rain event will generate runoff faster, and you'll have to operate the system more. But if you recall, with sea level rise, your structures are at risk of not being operated because you might have a higher tailwater condition. So that raises an awareness with the district and really creates the need for us to do or to plan how we will deal with this asset we manage in the presence of sea level rise. And so the key things to note from the introduction part of my talk is we have gravity structures that are vulnerable when you have sea level rise. They were built many, many years ago, didn't factor sea level rise in their design, and some of the considerations have since become obsolete. A lot of the areas inland that were supposed to be storage areas, farm fields that could be flooded frequently, are now cities, and they're discharging with infrequent rainfall events. We have future potential sea level rise, additional likelihood of storminess. And so all of these things made it necessary for the district to take some action. And the strategy we came up with is this program called the Flood Protection Level of Service Program. And it's a systematic way of tackling the issues we have raised, looking for potential adaptations and solutions, and coming up with a structured way to support decision-making to prioritize improvement in infrastructure. So I'm going to transition now to the level of service program. And again, I'm going to start you off by reminding you that we're part of a 3-tiered system. And the primary system is the piece we run. But for the system here to work, all 3 systems must work in concert. And the plans that are happening in the secondary and tertiary system must be compatible and consistent with what's happening in the primary system and vice versa. So to get us started, a little bit over a decade ago, while Obi was still here, we did an initial screening of vulnerability assessment at all of our coastal structures. Now, the work back then was focused on the design conditions, and we were able to look at how the structures were vulnerable to rising tides, higher tides, and storm surge. The loss of efficiency and the likelihood that these structures will remain closed at times when they should be providing stormwater getaway. And what we found was that the most vulnerable structures were on the southeast coast, mostly in Miami-Dade and Broward County, but really on most of the southern part of our system were structures that were vulnerable. And we've done some additional work since then to update that assessment with very, very current assessment of the low-lying structures. And the methods and approach that we used for this current work has been adopted by the Corps of Engineers, and they are incorporating our results as well as the results using similar method that they've done on additional structures in South Florida into the ongoing South Atlantic Coastal Study. The key findings of that study essentially are summarized here. We confirmed that the structures that were vulnerable remain vulnerable, and we categorized them in 6 groupings, depending on the severity and the nearness to potential loss of efficiency at the structures. And so with that in our background, we prioritize the basins across the entire district where we will be doing these level of service studies. We put together a program that allowed us to identify and prioritize the district's long-term infrastructure needs to be able to address flood protection, to come up with a systematic approach for assessing the level of flood protection needs within the 16 county region that we support. We make sure that the system allows us to identify at-risk structures and the areas where we are most vulnerable or where we have choke points that require improvements. And this could be to the canals or to the structures, or it might even be something that could be done with operations of the asset we currently have. We made sure that the process, which was a formal process, was integrated into the other works of the district, including a capital improvement program and an inspection program that allows us to go out and take a look at these assets on an annual basis to make sure they're performing as designed. As noted, we're part of the 3-tiered system, and it was important that whatever we did was coordinated with the operators of the secondary and tertiary systems, including local governments, the special drainage districts, and other agencies with responsibility for flood protection within the region. So how did we kind of scale out this program? We carved this out into 3 major phases. And we did this for a number of strategic reasons. We start with an assessment, and the assessment is an ongoing exercise that will continue in perpetuity. We intend to visit every basin within the district at least once every 8 to 10 years and make sure that we assess its ability to meet its flood protection needs. During the assessment phase, we identify the potential issues, and this phase is really targeting problem identification. It doesn't look for solutions yet, it's just identifying where we have challenges. And we prioritize the watersheds that we look at, identify what those issues are, and where we find issues that require solutions, we move into the next phase. And we've called these multiple things, resiliency study, adaptation studies, mitigation studies, or some combination of all of those works. But essentially, at this stage of the work, we will take a deeper dive at the problem that was identified during the assessment. And when we do this part of the work, we'll be looking at solutions to the problem identified, not only in the primary system, but also in the secondary and tertiary system. And a little bit more on this in a later slide. But ultimately, we want to, at this stage, get the work to the point where we have a recommended course of action or a preferred plan of action, and that we've done some of the preliminary work necessary to quickly move us into design and implementation of the project. And we structured this this way so that we don't end up with good plans sitting on a shelf, but we end up with actionable plans that could be quickly approved and implemented. The focus of our work over the last 5 or so years have been in assessments. And as we've done enough assessments, we're moving now into starting some of the mitigation studies. And later on in today's presentation, Dr. Zhao will walk you through a case study of some of the work that's done under the assessment phase, and also might speak a little bit about what we expect to do when we get into the adaptation and mitigation studies. So in a little bit more detail, these are some of the typical actions that will occur as we implement an assessment or a basin. And this is fairly comprehensive work. The focus during the assessment is the primary system, the system we operate. And we're trying to find out at this stage what the issues are with the system we operate, what problems we can identify that we need to resolve. It's a comprehensive effort that as I mentioned earlier, and we start by first of all compiling a multi-volume atlas for each of the basins we work into. This water control atlas has sections that deal with everything from the water management objectives within the basin, the assets that are available within the basin, not just within the primary system, but also within the secondary and tertiary system, the operations for those assets, their operational plans and intent, but also some really dry pieces of information that only engineers love, but we collect them all the same because most of my staff are engineers and we want to have them. These documents are available to the public. They're certainly available to our partners. Some sections have been redacted from the outward-facing documents because they may contain information that Homeland Security has decided we should not publish openly. Now, when that work's progressing, we also work on building models, if we don't have them already, that do the hydraulics and hydrology of the basins we're looking at. And these models are different from some of our long-term models that do period of simulation or period of record. These are event-driven models because for the purpose of the level of service study, our focus is on looking at design storms or specific storm events. So these typical models typically will cover a month to 2 months duration with enough setup time to get your antecedent conditions right. An event, a rainfall event or a storm, a historic storm or a design storm. And then enough time for the system to recover. And we're looking at what's happening across the entire system. We come up with an assessment using a number of different rainfall severity. So we're looking at the maybe 1% accident storm, typically the 1 in 100 year event, or a 10% accident storm. Some other storms that Dr. Zhao will talk to you about when she goes through the case study. And we simulate not only the design conditions that were in place when the assets were built, but also the current conditions that represent changes to date, including regulatory changes and development in internal areas that used to be farm fields. But we also simulate future conditions using a number of sea level rise conditions. In this case, we use 3 different sea level rise projections. And this is significant in that I didn't say we use a future condition matching a particular point in time on a rate of rise curve. We use 3 different sea level rise conditions, and that will become clear when I explain the approach we've taken for looking at sea level rise. With that, we identified at-risk segments, as I mentioned earlier, and features within our system that may need some work. We coordinate very tightly with our counterparts at the county during this phase of the work. Even though the look is on the primary system, we feel that it's important during this assessment to understand what's happening with the secondary system as well. Now, so what do we measure? How do we determine what's at risk? What are the metrics we look at to determine the level of service? We ended up with 6 metrics that we collect or we evaluate, and a lot of that came from some of the early meetings we had once we instituted this program. We talked to water managers, we talked to a bunch of different people about really what's the level of service, what does this mean? And the conversations came back very quickly. It's not A, B, C, D, E, like some methods that have been implemented previously that have no physical interpretation to things, but what also became clear, what the metric for level of service was quite varied depending on who we were talking to. So we ended up with 6. 2 of these metrics have to do with the canal. One looks at the maximum stage reached within the canal at any segment of the canal when the design storm or the simulated storm goes through. And it's not a snapshot in time, it is the maximum stage which could be arrived at different times depending on where you are within the canal segment. It essentially looks to see if you've exceeded the bank or if you've exceeded a phrase that we call the bank full elevation that Dr. Zhao might explain in a little bit more detail when she does the case study. We also looked at the discharge capacity of the canal capable of discharging the regulatory flows coming into it and the runoff that is likely to see. And we have a couple of metrics that look on the watershed on the land side. There's a more traditional, the maximum depth, the extent and depth of flooding that you see. There's also the duration of flooding. And I usually explain this by giving an example we had in Collier County or South Lake County recently. A 1-foot flood that happens over 2 or 3 hours that covers your streets and your yards maybe even gets into your garage, may be a nuisance, but may be acceptable. But if that same event persists for 2 or 3 weeks, then it becomes a life and safety issue, because garbage can be collected, maybe critical medication can be delivered because your roads are impassable, and really some bad outcomes could occur. So if under future conditions, if you have the same type of rainfall event, creating maybe the approximate same depth of flooding, but that depth of flooding persists for longer, we wanted to be able to know that. So that was an important metric for some of our stakeholder groups. And then the last two metrics have to do with the tidal structures themselves, how they perform during storm surges, and the ability to discharge the design flow. What have we done? We've completed studies over much of Miami-Dade, and we have ongoing studies in the rest of Miami-Dade. We've completed studies in part of Broward County and have ongoing work at the assessment level in just about the rest of Broward County. And we've done work in the majority of Collier County. And these are some of the priority areas we identified. And when the assessment's done, I mentioned that we're going to the next phase, which are the adaptation studies. And here are some of the things that you typically will see when we do mitigation, adaptation, and mitigation planning. The focus shifts from the primary system to now include the secondary and tertiary system. And the modeling that has to be done is more robust. If you think about it, for the primary system, we're looking at our assets, and the modeling we need needs to be able to cover the hydraulics and the hydrodynamics of those systems. When we start looking at the potential solutions, and you are considering things such as nature-based solutions, some of the modeling tools we use may need to be different to look at the impacts of mangroves or some kind of vegetation on mitigating storm surge. We may need to step out of some of the tools that we've historically used in our assessment phase of the work. For this phase of the work, it's a public planning process. And for those of you who are familiar with the course work, it's like doing a PIR where we have members of the public, members of the key stakeholder communities be present in workshops and public meetings. And we engage very closely with counties, drainage districts in trying to understand what their short and long-term plans are for addressing flood protection issues within their parts of the system. One critical piece of this work is to be able to evaluate alternatives and rank them with the no action alternative. We have to have an understanding of the damage that would occur with no action, and the damages that you can see, or the damage reduction you can expect to see with some of the alternatives. So damage assessment is a critical piece once we get into this phase of the work. Another very critical piece is, how do you sequence your courses of action? Do you do everything at once? Do you take some courses of action first and then some later? How do you bring the potential courses of action together in a combination that provides you the best outcome for the region that you're looking at? And then, as I mentioned earlier, we advance the work to some preliminary design level consistent with the basis of design state, such that when we're done with this part of the work, it becomes an easy lift to get. We have the costs, we have the benefits, we can get the justification going, we have enough to support funding decisions that will allow us to move quickly to design and ultimately to construction of this critical infrastructure. And so some of the things that you might be looking at that stage of the work could be the example here in one of our structures. This is S26, where the gravity spillway, which is the leftmost structure you're looking at, is being supported by a pump station. And so as you see in the inset to the top right, at some point when the structure has to be closed because of tailwater conditions, you could turn off the pumps and you create some positive discharge and address some of the stormwater needs during those periods. There could also be other, green or more passive type solutions. This picture to the bottom right is showing a higher seawall, but in some cases that might not be a gray infrastructure. It might be some kind of living seawall that's part of a nature-based solution that's been proposed. But in the second phase of the work is where you will see this type of investigations looked at very carefully. So that pretty much covers the key two steps. We're beginning to do some work in what we call phase 2 of the mitigation studies. And we're hopeful that we'll be able to launch into phase 3, which is design and application of some of these solutions with some recent BRIC grant applications, building resilience grant application we put in recently. Now, a couple of things we do or techniques that we've deployed that are not traditional, but that we like a lot, and that we hope to see implemented in other areas, are this concept of the adaptive resilience model and the adaptive resilience planning. And I'll spend a little bit of time describing the graphic you're looking at here. So I mentioned earlier that multiple people create sea level rise, rate of rise curves, and on this graphic, the red line and the green line could represent two such curves. With traditional planning, you pick a curve and you design, you plan and design to conditions in the life of your project. So maybe 50 years out, you look at the sea level rise and you do your design to that. Well, there's some uncertainty with regards to the rate of rise. And what if you were wrong? What if you were on a different curve? Your design will be great for the curve you were on, but may not be the most optimal design for the reality that you face. And so when we faced with that challenge, we took this approach that said, instead of designing to some future condition, let's find out, and this works for our structures, but let's find out the level, the sea level at which our structure starts becoming inefficient. And once we've identified that, we can then trace that onto a sea level rise curve and figure out how far out that's likely to happen. Now, once we're doing that, we also look at, throughout phase 2, we look at, so what kind of solutions are we likely to propose and how long does it take to implement those solutions? And for the purposes of discussion today, let's say it takes 10 years to implement a replacement pump station or a replacement structure. With those two pieces of information in hand, at the level at which things are likely to fail, you can pick a curve, any curve. In this case, I'll pick the red curve, which is the more critical of the two curves. And I'll trace on that curve my level at which my structure starts to fail or becomes inefficient. Then from that curve, I'll work backwards, the length of time it takes to implement my adaptation. And that'll give me the threshold or the trigger level, which also is on the red curve, at which I need to start my action, which could occur sometime in the future from today, or maybe past, depending on what you see. But with the graphic that you're seeing there, it's sometime in the future. And what that tells us is for our decision makers, you tell them, when you see this condition, this trigger condition occur, we need to initiate adaptation such that by the time the conditions become inefficient, adaptations are in place and ready to implement. So what happens if we were wrong and the rate of rise isn't so aggressive and it's what's on the grain curve? Well, the trigger condition will just occur later, and I need to take the next step may occur later. What if it's more aggressive? Well, you don't have a curve for that, but it just means that trigger condition again will occur earlier, and we'll be on notice that things are happening so fast that we'll need to shrink the time it takes to plan and implement our adaptation. So this strategy essentially is the approach that we've chosen to use, and it's something we use actively with the level of service program. Now, that is the model, and the way that happens with our planning is what I'm showing in the next slide here. So, and what this tells us is, so we have this model that we're comfortable with, and I'm going to hang up this phone. I think somebody's desperately trying to reach me, but you'll have to wait. So what you're looking at here is essentially the method implemented with a realistic plan. Take a look at the lowest green line. The lowest green line represents maybe a low threshold event. And at that threshold event, on this graphic, approximately about 3.6 feet of sea level rise, things may be inefficient enough, but may be possible to address with an operational change. And so all you need to do at that point is walk backwards, find out the correct level at which you need to have a new operation plan approved, so that by the time you hit that threshold, you have new operations in place that address that low threshold event. Similarly, there are some solutions that are not going to be resolved by changing how you operate. You may need to change your regulations, maybe build higher seawalls, maybe actually do something different, and combine those with operations, actually make some structural changes. Well, that's key too. And you find out the appropriate threshold for that inefficiency happening. You work backwards and find out the appropriate threshold when you want to start action. And likewise, for things that even go beyond needing operational changes, maybe a retreat strategy or some major retrofit, elevating roads, elevating buildings. And again, you use the same type of model. And so we have a planning strategy that incorporates that model into our overall strategy. And so how do you know how you sequence through each of those potential solutions? How do you know how you transition from operations to a combination of operations and regulation and some infrastructure changes to major modifications of the system? And this is where how to make decisions, especially in this environment where there's uncertainty, came into play. And this was one of the things we started looking at when Dr. Bisekera was here. I invited, I think, Rand Corporation, I think Robert Lampert, to come do a workshop here on robust decision making. And in the time since that workshop, we've continued to work with others, including the Dutch and Deltares, on a process called dynamic adaptive policy pathways. And what this strategy does is allows us to really lay out the different potential pathways to address the potential outcomes, factoring in risk so that we don't completely ignore the uncertainty in this system. There is a very great book on this, and I think there's a link to this in this presentation. The link I'm sure Mario will be glad to share with you. It's a free book. It's called Decision Making Under Deep Uncertainty, and it has paragraphs or sections in it, chapters for both the dynamic adaptive policy pathway and robust decision making. And there's also some great videos on YouTube that include some of the work we have in here. But the example I typically give is that for one of our coastal structures, if you were going to go ahead at that structure and perhaps build a pump station to help or facilitate stormwater discharge when that structure is closed, you may end up, when you're doing the analysis, determining that for a high level of sea level rise, maybe you need 3 pumps. But you will not get to that high level for the next 20 or 30, maybe 40 years. So when you go implement that project, you don't build the 3 pumps right away, but you might acquire the property for all 3 pumps. You might even put in the base for all 3 pumps and then just install the first pump. And if your rate of rise is as planned or as projected, at some point down the road, maybe in 10, 15 years, you could install the second pump into the open bay and install the third pump at some point in the future. If the rate of rise is faster, maybe you install the second pump in 5 years. Or if you don't trigger the condition for the second pump, you're lucky that you haven't built all 3 pumps because you can need to use the first pump well past the period when you thought you'd have added the second. Another example that we actually came across recently in one of our projects was where you're going to build a reservoir where you need storage that can be met by a 4-foot deep FEB today. But in the future, you might need a 12-foot reservoir, 12-foot deep reservoir, 16-foot deep reservoir. Well, if you design your levees for a 4-foot deep feature, you're going to have to take it upline, maybe knock down that levee and build a much bigger levee when you need a 12-foot deep reservoir. But you could start your design with the foundation for a 12-foot deep reservoir, build it high enough to do a 4-foot reservoir, which is going to be fairly expensive for a 4-foot reservoir, but allows you when the time comes to transition to a 12-foot reservoir to save significant cost in the future. So there are things like this that are looked at. These are not theoretical things you do off by yourself. There are things that you work with major stakeholders and some of the decision makers. And what the dynamic adaptive policy pathway does is it gives you a framework for engaging that type of decision making. And it's a great new technique pioneered by the Dutch, but that we've taken on and we're implementing in collaborative work. I think FIU has been part of this efforts with Deltares as well. So there are a few other things that support the level of service program. And some of these may represent areas of research interest for you. For today's work, we're very concerned about the downstream conditions that are coastal structures. And we've used some simple methods to estimate what those conditions will be, especially in the future. But as we get into some of the design level work, it's become more important to be able to do some storm surge modeling with actual, maybe putting in a few actual hurricanes or some selected storm conditions to see what the tailwater conditions of the structure would be. And it's not enough to just look at the ocean conditions. We might need to actually route some of those waves all the way through narrow canals to see if they're amplified by the time they get to their structures, or if they're muted or dampened by the time they get to our structures. We're concerned about future rainfall scenarios. For today's conditions, we know what the current rainfall is. And as Obi mentioned earlier, we're dealing with things that are non-stationary, and rainfall conditions may change in the future. And for us, we care about not only the extreme events, which we need for the level of service type work, but also the average conditions, not just the pickedness of the system, but the average occurrence of rainfall. So the possibility of helping develop some future rainfall scenarios is something we're very interested in and that we're working with FIU on, as well as the USGS. We're also looking at district-wide, just getting some of these standardized future scenarios using whichever best methodology. There's some work recently done in California, and Obi mentioned the Dutch approach, which will support multiple efforts within our 16 county area. One of the things we're also concerned with is, well, we've talked about groundwater as changing. We've talked about rainfall as being highly dynamic, and we need to be able to look at extreme events, look at some rare events, maybe 1 in 10, 1 in 100 year type like events. Well, some of these things happen together. And how do you deal with decision making when you have these compound events? So those are some of the areas of challenges that I mentioned on this slide, and we're working on some of these. We continue to be open to work with academia and others on everything that's on this page. Future climate scenarios, as I mentioned earlier, including rainfall, rate of sea level rise. And by the way, I mentioned rainfall, but temperature is also of great interest to us. Rate of sea level rise, again, we want to be able to get as good a projection as possible. The correct groundwater levels to use for initial conditions, because this has a great effect on your projected flooding or flooding risk. Storm surge protection at our coastal structures, like I mentioned earlier, and then compound effects, the compound events where you're looking at the compounding effects of rainfall, storm surge, and groundwater levels. And we need to be able to answer the question, is a 1 in 10 rain with a 1 in 10 surge, which could happen together, a 1 in 10 event, or is it rarer than a 1 in 10 event? And it's quite possible that you could have a storm surge without the corresponding rainfall event. And how do you deal with those combinations? Project funding, it's no good doing this great work if they don't become projects on the ground. Nothing gets solved by just knowing until you can actually do something. And that's an area we're always looking at. And we welcome grant opportunities and partnerships. And then how do you facilitate decision-making? And this is critically important to us. One of the things that I've seen in my career is that sometimes you have some great inertia to doing big projects that are extremely expensive. And if you can find a way to help decision makers make the no regret decision and the first decision to get the ball rolling, it makes it a lot easier to then make the next one and the next one, and ultimately to make that hard decision which looks daunting at the very beginning. And that's why the DAP approach is one that we've adopted to some degree, and we hope will help our decision makers when that time comes. And so going forward, I have a number of things I'll run through quickly, and then I'd like to save the ground to Hongying, and I'd like to set it up so that we take questions after both Hongying and I have talked. But again, our focus is looking at science-led planning and studies. We're focused on getting the entire district covered with our assessment, and doing this every 8 to 10 years, and then moving on to those basins where we've identified issues as soon as the issues are identified. Moving on quickly to improve technology engagement with the local stakeholders and academia to start addressing some of the problems we find and coming up with techniques that will help us to be better suited to do our assessments and robustly look at solutions that work in the short term and set us up nicely to be able to continue to solve the problem in the long term with the uncertainty in both the data and the inputs to the system. And we're ready to face this challenge very squarely and to make the investment needed. And to that end, we have the support of our leadership. The governing body is extremely supportive, and my executive leadership team is on top of this. If you're tracking at the state level, I think the governor put in a resiliency ask in his budget, which we're very excited about. And we think over the next few years that we'll be making great strides in addressing the flood control needs and the resiliency of the flood control system within this region. And with that, I have a question slide. I had to show you something that had some flooding in it, but I'd like to pass this on at this time to my colleague, Dr. Hongying Zhao, to go through the case study.
Good morning, everyone. How do I share my screen? Okay. Hi, Mario. Can I share my screen?
Yes, if you click on the bottom of the Zoom meeting, you'll see a share screen button.
Okay, I saw that.
So click on that, and then you should have the ability.
And then Hongying, when you click on share screen, it'll give you options of what screen. You select the screen you want, and then at the bottom of that box, you have to hit the share button.
Okay. Can you see it? Can you see my screen?
Not yet.
Not yet.
Okay, I'm always having this.
So you have to hit share screen within the Zoom, and then that'll bring up another. That'll bring up another box. There you go.
There we
Right
go.
screen.
Perfect. Thank you.
Okay, very good. So good morning, everyone. My name is Hongying Zhao, and thanks to Mario for the very nice introduction. Akin just summarized the mission of the district and overall picture and the different aspects of the level of service program very well. Okay, so I'm just going to, in my presentation, I'm just going to share with you two typical level of service projects. Actually, we just completed these two projects. The first project I want to share with you is C8 and C9 watershed level of service project phase 1 study. This study area includes two basins. One is the C8 basin in South Miami-Dade County, and another one is the C9 basin in the Broward County. The objectives of this phase 1 study are to develop and calibrate an H&H model for these two basins, and also use this model as a tool to assess the current condition and the future sea level rise condition level of service the basin have. And for the future conditions, we assess the future groundwater level, future sea level rise, and the storm surge, and future land use. And we also include the two future projects planned. One is the American Dream Mega Mall plant and the surrounding commercial properties. And another one is the C9 C11 impoundment project planned by the Army Corps. So this is a slide Akin also just talked about the 6 flood protection level of service performance metrics we use to assess the level of service for each basin. So I'm not going to repeat this slide. And this slide shows the level of service assessment result for PM1 and PM2. The chart on the left shows the PM1 assessment result, which shows a peak stage profile along the C9 canal. The circled area shows the bank exceedance under different sea level rise conditions. Some examples, we can see at the downstream of Highway 441, North Bank exceedance for the 1 foot sea level rise 10-year event. Also South Bank exceedance for the 3 feet sea level rise, 2 feet 10-year event, and 2 feet sea level rise 25-year event. And we can also see from South Flower Drainage District Pump Station S5 to Highway I-75, South Bank exceedance for the 3 feet sea level rise and a 5-year storm event, or 2 feet sea level rise and a 10-year event. So these are some examples we identified for the PM1 assessment. The chart on the right side shows a Pn2 assessment result. This chart shows the 12-hour moving average peak discharge for a 25-year event under current and 3 future sea level rise conditions. And the discharge capacity is measured by CFS per square mile. The reason we choose a 12-hour moving average is because we wanted to filter out the effect of tidal effects. So this chart shows clearly that the 12-hour peak discharge in the canal are sensitive to all sea level rise conditions. And the 2 feet sea level rise condition, we can see the discharge capacity likely reduced from high 20, about 28, to low 20s in terms of CFS per square mile. And this picture shows some assessment results for Pn3 and Pm4. Pn3 and Pm4 assess the peak flow capacity through the structure and the different scenarios. So we assess the we actually assess Pn3 from different angles. We look at the peak headwater, peak tailwater, and also peak discharge, and how do they compare? How do these values compare against the design conditions? If you look at the chart on the lower left side, it shows the peak discharge and the relevant headwater and the tailwater. For a 100-year event under the 3 feet sea level rise condition, the peak is about 22 or 2300 CFS. It's actually about 50% of the design capacity. The headwater also exceeded the design headwater for this structure. The chart and the table on the right side shows the peak discharge for different events and different sea level conditions. And we can see clearly the impact of sea level rise. The peak discharge is reduced from current condition to 1 foot, 2 feet, and 3 feet sea level conditions. And this table actually summarizes the peak discharge, peak headwater, peak tailwater, and also the head difference for different scenarios. And we can see decreasing for all of these parameters. And this slide shows the PM5 and the PM6 assessment result. The map on the left side shows the flood depth distribution for these two basins, and the map on the right-hand side shows the flood durations for these two basins. And these two, we actually have GIS grid file, so you can zoom into each, to any interested area. You probably cannot see a lot from these two maps. But in the GIS, you can see it clearly. And we also produce a summary table to quantify the impact of the sea level rise. In that summary table, we actually quantify and the different flood depths, what is the acreage of area flooded, and what is and the different flood duration, what is the acreage flooded. So which give us a very clear way to quantify the impact of sea level rise. So for C8 and C9 study, which this project, this phase 1 project actually completed January 2021. So for under existing condition performance, we established the existing condition performance against the future conditions with impact of land use change and sea level rise. In summary, C9 generally function at about a 25-year level of service level, and the bank exceedance occurred in several locations under sea level rise conditions. The 12-hour peak discharge at the S29 structure for all storms are sensitive to all sea level rise scenarios. And also we see multiple areas performing poorly based on the PM5 and PM6, but they did not correspond to the bank exceedance in PM1. This one can help, and we can infer maybe there's some deficiency in the secondary or tertiary systems. So for the next step, Akin also talked about that. We are planning to implement a phase 2 study, which is called the C8 and the C9 level of service adaptation planning and mitigation strategy project. And the objectives of this phase 2 study is to use the model tool developed in phase 1 to assess the impact of potential projects on improving flood protection level of service. And also under phase 1 study, we want to do economic analysis and do some adaptation strategy planning. So we plan to kick off this one very soon, maybe in the next 1 or 2 months. And the second project I want to share with you all, Akin also talked about it, is the low-lying tidal structure assessment, susceptibility to sea level rise and the storm surge. Under this study, we assessed the 27 tidal structures. And there's another nice tidal structure is going to be assessed by the Army Corps. In this project, 7 structures is in Broward County, and the remaining structures are in South Miami-Dade County. The pictures on the bottom shows some tidal structures, and I think these structures are mainly in Broward County. So in this assessment, we mainly wanted to design a scenario for design flow and also 6 surge events, and also these 6 surge events is from 2-year, 5-year, 10-year to all the way to 100-year storm events. And we also want to assess current sea level and 3 sea level rise scenarios. Then we wanted to plot the assessment result to this sea level rise projection to quantify the susceptibility of each structure. So in this study, we selected the HEC-RAS model as a tool, and we simulate the design flow, and also we simulate the surge and the sea level rise conditions. This picture on the left side shows the HEC-RAS modeling diagram for S29 structure, and that's a picture on the top is S29 structure. And then we project those, plot out those results on the sea level rise projection curve, and what we can get is for S29 structure, the bank 4 stage we reached for a 25-year event with 1 foot sea level rise. And then we did the same type of analysis for the all 27 structures, and based on the assessment result, we can determine the adaptation priority, and the intent is to use this result in combined with other criteria like the structure conditions, drainage area, aging, or dimensions. All of this will be taken into consideration. So this one is a high-level summary of the second project I wanted to share with you all. But before we go to the Q&A section, I do want to spread some rumors, and Akin can correct me. I think, like Akin mentioned, our goal is to cycle through the entire 16 counties in a 10-year period. So we actually have a lot of work, and can always use some help. And I believe district sponsors some summer internship programs. So if you are interested in this type of program, you may submit your application. And we love to have students on board to share with us your insight and your new ideas. So I don't know, Akin, do you have any more information to share about this summer intern program?
I think I'll just let you put that out right now. And then as we approach the summer, we'll see how many students or how many people we get to take this year.
Very good. Yeah, I can take some questions, and I think Akin, you can also answer some questions, right?
So thank you all very much. Mary, I think we'll turn it back to you, and we'll be glad to answer questions or engage with the audience as necessary.
Thank you very much. That was a really fascinating presentation by both of you. We have at least one question in the queue. I will exercise the moderator's prerogative and start with one quick question and then a more extended question. And just the quick question is, how are you collecting data on sea level rise? And if I could ask Hongying, if you can stop sharing your screen, or maybe I can do that for you. Let's see. Yeah, then we can get back to it. Great. Thank you. So how are you collecting this more granular data on sea level rise in the South Florida area? Is it by gauges?
Akin, you want to answer that question?
Sure. So at each of our structures, we collect with gauges, headwater and tailwater elevations, and that's the extent of what we have. But we rely on data that's collected by others offshore to do our analysis. So for much of what we do, we rely on information collected by NOAA, by other researchers doing sea level rise work. But at each of our structures, we do have high resolution, I think at 15 minutes or more frequent water level data for both headwater and tailwater to help with operation decisions.
Okay, thank you. So then my general question is, if I understand the system that you've described, we know that obviously sea level rise is very gradual. It's been going on in the charts that you showed, it's been going on for the last 100 years. But it seems like, as I was watching your presentation, it seems like there could be tipping points of system failure where the results would not be gradual, and where you would have a really catastrophic, where you would have a combination of rainfall and storm surge, or rainfall and even high tide, or some combination of these factors that could reach that one tipping point where you have a system failure and the results are really catastrophic. And could you describe what that sort of catastrophic scenario would look like for residents of my neighbors here in Surfside, Florida, residents of Coral Gables? I know that Todd is worried about this. Todd Crowell is worried about this as well. So just what would we be looking at if you have a system failure like that at one of the points?
Hongying, do you want me to take this too?
Yes.
Okay. So first of all, we want to make sure we don't have that type of situation, which is why we have this forward-looking approach. But the approach we've taken with the analysis, there are two ways you can have this failure. If you're looking at sea level rise, typically we expect that would be gradual. That would be something that would eventually rise to a point where your structures just have to remain closed. And when they're closed, they're not providing flood protection. And when they're not providing that stormwater discharge, what you'll see is the secondary and tertiary system start to get more and more flooded. There are examples in recent history where we've had to keep the gates closed. That kind of gives us an insight into what this might look like. But as Hongying mentioned, there are actually conditions right now where the primary system is fine, but we're still seeing the secondary system flood. Now, the second possibility that you've described is something that may happen more from surge than sea level rise, where you have a sufficiently high event. During the storm that stopped in the Bahamas was one that scared the bejeebers out of us, where you could have storm surge in the order of 15 feet, which will not only cause the structures to be closed, but will overtop the structures and may actually destabilize the structures. And so we're concerned about those type of conditions, and we have a completely different effort or strategy that's ongoing with our resiliency program, looking at things like that. And there's a planned project with the US Army Corps of Engineers. It has a number of different names, but it's a revisit of the Cnsf system that we had hoped would be funded and started this year. We hope it does get funded and started pretty soon, that people within the region are advocating for. I think those studies, including such efforts as the back-based study that the core is doing right now in Miami-Dade, will be the things that will deal with the more catastrophic storm surge related type of failures. But for the level of service program, our focus is on the current asset that we have and ability to make sure it continues to work in the long term, and the kind of infrastructure needs we will have to be able to deal with sea level rise and developmental changes.
Great, so thank you very much. Well, anyone who'd like to ask a question, please raise your hand. I actually don't know how to do that myself in Zoom yet, or I have to relearn it every time. But please raise your hand or send me a chat, or perhaps just speak up. While people are getting their questions together, there was a question that David Jimenez Gonzalez asked about 20 minutes ago in the chat box. He asks, to evaluate the actual exceedance probability of these various events, do you use multivariate distributions, cupulas, simulated time series? If you look, it's a somewhat detailed question, and if you want to just take a look, either of you, Akin or Hongying, back in the chat screen to answer that sort of statistical question, data analysis question.
Hongying, do you want to take that one?
I think you have answered for that question.
Okay, I could. So yeah, for right now, that is, especially when I mentioned the compound events, I know that that's an area that we're spending a fair amount of time with, I think, faculty from, is it Central Florida, or what's the school again?
Central Florida.
Okay,
Yes.
and so I think they are looking at cupulas for that, and
Yes.
this was an initiative, and I think Obi wants to speak to it, because Obi is quite familiar with this study. I think it was one that we started while Obi was still here. And Obi ran that project.
Yeah, yeah, I can talk about it. You know, when I started that project with the University of Central Florida, the idea is, you know, we have storm surge, we have rainfall. The whole issue is, how do you account for joint probability? Because you cannot assume 100-year storm surge and the 100-year rainfall will coincide. You know, the joint probability. So this compound flooding, which is also of interest to American Society of Civil Engineers, and I'm a part of the committee at the national level on that. How do you come up with a standard practice? And an interesting aspect of that UCF study we started, and that's continuing, is, you know, not only we have storm surge and rainfall, but we also have rising groundwater table. It's like I say, multiple threats from all sides. How do we address this joint probability of all these threats? I think that's the goal of that study. And one of our students, Francisco, is actually applying that tool that was developed by UCF. He's in the institute doing a PhD to look at that compound flooding aspect of Arch Creek Basin right now. But yeah, and the other thing, to comment on what Akin mentioned is, you know, step jumps in sea level rise, I know has been you know, hypothesized. Even, you know, Harvandas and others have talked about it. You know, that is still you know, debated in the community, but there are some evidences from many thousands of years ago that may have happened. But even then, it probably would happen over 10-year, 20-year shorter period. We'll have enough time to respond to it. So I think it's the storm surge that Akin talked about, you know, Hurricane Andrew-like situation. How do you account for, how do you manage the, look at the resiliency in that kind of catastrophic flooding situation, which is important for our financial program, and perhaps look at the damages that might be causing, not only the physical damage, the social, economical damage that might occur.
Great. That's really fascinating. So we have another question from Henry Viceno. We at FIU are implementing an operational hydrodynamic and water quality model for Biscayne Bay. Hopefully we'll be ready this year. I wonder what kind of joint collaboration could be instrumented with the district to link the model to underground waters and stormwater network. What do you think, Akin?
Yeah, first, I'm not certain if this is something that we've engaged on already, but we are particularly interested, us and the Corps of Engineers, in looking at Biscayne Bay right about now, because there's a major SERC project, the BBCR project, that's ongoing. And that model is particularly interested in looking at both the land side, the bay side changes that would occur over the next several decades as we look at implementing restoration projects. So if there's something, and I believe FIU may actually be on the team with that. I'm not sure if this is the particular model you're talking about, but I believe that this is something we'll be interested in as part of that project. And we may be collaborating with FIU already. So I think the key will be to make sure that the right hand and the left hand are talking. If there's a tool you have already,
I think we have two projects going on. It's the one that you just mentioned, BBC, that I think Tiffany is leading the collaboration with the Water Management District on the southern Biscayne Bay, as I understand it. And the other one is the Army Corps of Engineers Back Bay study that we have funding from the Army Corps, where we are trying to link the watershed models and flood models to water quality models in the Bay. And I think that's where I think we, internally we can do that collaboration as well with Henry's efforts. So there are, there's a lot of interest, with the attention to Biscayne Bay, there's a lot of interest from FIU to collaborate on this type of work. So we would be open to any other opportunities to, particularly this linking watershed models to ocean hydrodynamic models, I think, what we call land-ocean interaction aspects.
Great, thank you. So I think we have time for one or two more questions. Does anyone want to jump in?
I wanted to ask Hongying a question. I think I'm glad the C8, C9 and are finished. Some of them are also tributary to Biscayne Bay. That study, do you know if those reports and models are available for our students if they want to do further analysis?
Yes, the report and the model actually are archived in our SFWMD system, and anybody can download the report and the model.
Okay, that's wonderful. Thank you.
Any other questions? Can I ask another question, Akin? You mentioned that the South Florida Water District has applied for a FEMA grant, I believe. Could you go into the details of that grant program? Is that under the BRIC?
That's correct. We have two projects that we're applying for as part of the BRIC, building resilience infrastructure, and we're looking at the S29, which is in the C9 basin, and the S27, which is in the C7 basin. And we're looking at the opportunity to support these gravity structures with forward pumps, similar to what we have in the S26. That effort is being led by a resiliency officer, Dr. Carolina Moran. I think you know Carolina, and we're very optimistic and hopeful that between the grant and the governor's initiative, that we'll be able to advance these projects.
Fantastic. Well, that's an important new facility. For those of the students, just for a benefit of background, and I was able to observe this up close in the administration recently, FEMA administers a series of grants that under basically the disaster mitigation framework. The National Security Council staff has a directorate that's called the Resiliency Directorate. And it oversees all of these FEMA disaster mitigation kinds of programs. Within that framework, the FEMA programs, if you remember back to Hurricane Katrina, were all focused on disaster recovery. And of course, as policymakers realize the kinds of disasters that are possible moving forward, they shift from disaster recovery to disaster planning. And so the BRIC program is a new program that hopefully represents a trend towards the federal government, leaving in place and strengthening the disaster recovery kinds of efforts, but investing more and more in the resiliency kinds of efforts that are necessary to prevent catastrophes or to minimize the damage from catastrophes in the first place. These programs are they're very well designed, but it's very much a moving target. There are people, whose average age is lower than the average age of the people on this Zoom call, who are working on these programs, both in congressional committees and on congressional staff, and at the White House and at FEMA. And these programs are being designed right now as we speak. They're being modified every year. I mean, I think BRIC was the first time that it was launched was last year or the year before. Very important new facility. Similar new facilities are coming online, and so I would just recommend to everyone who's interested in working on these, that you become aware of the programs that there are. If you are interested in an internship with the South Florida Water Management District, they can use your help. If you're interested in getting really ahead of the curve and getting into the program design of the programs that FEMA administers, like the BRIC and so forth, I think I saw Carlos Becerra on the call. We've got many opportunities in Washington, D.C. and in Tallahassee to get into the weeds of the program design for these programs moving forward. And I think I can predict, or I should say, I hope that the trend that the BRIC program represents will continue into the future of a greater and greater attention on the kinds of resiliency investments that we really urgently need in South Florida. So with that, I think, do you have any closing comments, Obi or Akin or Hongying?
No, I think this is great. I want to thank Akin and Hongying and Mario for organizing this. I think this is the kind of needed interaction we need from the local level and the academia with the regional agency like Water Management District. There are many research opportunities that we could, help develop the tools for them to use the latest technology in planning and designing. And Akin mentioned that how to handle the uncertainty. I think that's an important area we are pursuing as well. We think that's the way to go in the future because of a lot of uncertainties in climate change projections. So this is great, I think, to have this kind of interaction and exchange.
Well, thank you. Yeah, sorry, Akin.
Mario, I want to thank you and FIU for creating this opportunity. We love to talk about what we do and what we're doing. I think it's the most exciting work out there, possibly. So we're always looking for the opportunity to share, and especially with folks who may be able to help us as we kind of explore how to best respond to flooding within this region. So thanks for having us. We'll be glad to come back if you need us again, and we'll hope to keep engaged with your team.
Thank you. You may regret that offer because we will certainly be taking you up on it. Hongying, do you have any last word?
No, I also want to thank these great opportunities. It's a pleasure to share our project with your team.
Fantastic. Well, we're very grateful. We hope to be able to post your slide presentations with your permission on the landing page for this event, along with a recording of the event itself. I think it's a great research opportunity for those like me who weren't quite able to capture all of it and want to be able to go back and study and keep learning from the presentations that you made. We will have that opportunity. So thank you all very, very much for joining. Have a great weekend, and I will see you soon. If anybody has any follow-up questions, please email me. I've provided my email in the chat box. Otherwise, I think our meeting is adjourned. And for those of you who are still at work, please take this invitation to take the rest of the day off.
Thank you.
Thank you very much.
Thank you.